All right, so we've all seen those totally mind-blowing AI demos, right? But have you ever stopped and wondered what actually goes into turning one of those cool tech demos into a real solid product? Something millions of people can count on day in and day out? Well, today, we're going to pull back the curtain and look at the real engineering journey behind it all.
Yeah, that's the big question we're diving into. How does that happen? Because it's definitely not as simple as just flipping a switch. It's this whole complex, really fascinating process of evolution, just packed with challenges and some super clever solutions. So let's get into it and see how it's really done.
Probably the best way to wrap your head around this is to think of it like building a skyscraper. Seriously, you don't just stack floors on top of each other, right? No, you've got to build this incredibly complex system, layer by layer. You pour the foundation, then you add the floors, the plumbing, the electrical, and with each new layer you get these amazing new capabilities. But, and this is the key part, every new layer also introduces brand new ways for things to break. Entirely new failure points you have to worry about.
All right, so here's the plan. This is our roadmap for today. We're going to trace that whole evolutionary journey of an AI system, starting from, the real basics and building all the way up to a complex, powerful agent. Let's get started.
Okay, first up, the AI production journey. The main thing to get here is that building a real AI isn't just a one-and-done thing. It's a step-by-step evolution. It's kind of like climbing a ladder of complexity. And with every single rung you climb, you need smarter, more sophisticated engineering just to make sure the whole thing doesn't come crashing down. And this ladder of complexity right here, it perfectly shows that progression. And it's not random at all. Most AI products actually follow this exact path. Think about it. You can't really make a system fast and efficient before you've made it safe, right? And you definitely don't want to give it the power to do things before you have a way to watch what it's doing. Every step really does build on the one before it. Which brings us to section 2, getting the basics right. So if we go back to our skyscraper analogy, this is the really critical part. This is pouring that solid concrete foundation and installing all the safety systems. The fire alarms, the security cameras. These are the absolute must-haves to make the AI useful and, more importantly, safe from the get-go.
Okay, so the very first problem you run into with a brand new AI model is that its answers are just, well, they're super generic. The solution? It's something called context construction. And it's basically what it sounds like. You're giving the model the right information it needs for the job. It's like giving it the specific blueprints, or access to the right data, or even tools like web search. Honestly, it's the difference between asking a random stranger on the street for financial advice versus asking your personal accountant who has all your documents right there. One is just guessing, the other gives you an intelligent answer. It's been called feature engineering for foundation model.
Now, this is really interesting because you have to think about AI safety as a two-way street. On one side, you have input guardrails. Think of these as a shield protecting the system from the user, blocking nasty prompt attacks or stopping someone from leaking private data into the model. But then on the other side, you have output guardrails. These are all about protecting the user from the system, catching things like hallucinations or toxic garbage before you ever see it.
So the key takeaway here is that you can't just cross your fingers and hope for the best. Things will go wrong. It's inevitable. So you need a playbook. For example, if the AI spits out some garbled nonsense, hey, maybe you just have it try again. Simple enough. But what if a user is getting really frustrated, or the situation is super high stakes? Well, then the best move might be to smoothly pass them over to a human agent. It's all about matching the right response to the right kind of failure.
Okay, so our skyscraper has a solid foundation. It's got security systems in place. It's safe. But what happens when a million people suddenly show up and want to use the building all at once? Well, that brings us right to section 3, scaling up smartly. This is where we install the elevators and the air conditioning, the core infrastructure needed to handle a massive load efficiently without breaking the bank.
So, as your AI product gets more and more popular, a totally new problem pops up. You realize that using your biggest, most powerful, most expensive model for every single little question is, well, it's like using a sledgehammer to crack a nut. It's just way too slow and costs a fortune. So what happens is these systems evolve to use a whole mix of models, big powerful ones, small fast ones. But that creates a brand new challenge. How do you know which model to use for which task? Okay, so one of the smartest tricks engineers use to speed things up is something called semantic caching. The idea behind it is actually super simple. If two questions basically mean the same thing, why would you do all the work to calculate the answer twice? It's a waste. So instead, the system takes a new question, say, what's the weather in London, and turns it into a kind of mathematical fingerprint, a vector. Then it quickly searches its memory to see if it's already answered a question with a similar fingerprint, like, tell me London's weather. If it finds a match,
bam, it just grabs the old answer from the cache. Saves a ton of time and money.
I mean, that sounds pretty perfect, doesn't it? A simple way to make everything faster and cheaper. But you know how it goes. With everything in engineering, there's always a catch. There are hidden complexities and some pretty big trade-offs you have to think about.
And here comes the reality check. The big takeaway is that there is no free lunch. Semantic caching can actually be pretty fragile. The search itself can use up a lot of computing power. And honestly, the biggest issue, it can be really risky. If you're not incredibly careful with how you build it, you could accidentally leak one user's private, personalized information to a totally different user. And that's a disaster. So it has to be done with extreme care.
This all leads us to Section 4, Power, Risk, and Agency. Okay, so our skyscraper is built, it's running efficiently. Now, we're about to give it the power to actually do things in the real world. This is the moment our AI stops being just a helpful search engine and starts becoming an active participant.
And this is the moment where everything changes. We're not just asking the AI for information anymore. We're giving it what are called right actions. That means the ability to send emails for us, to place orders online, maybe even to, start a bank transfer. We are literally putting the AI's hands on the wheel.
And this quote, it just says it all, doesn't it? The second an AI can actually act on its own, the potential for things to go badly wrong just explodes. I mean, getting a wrong answer is one thing, but a wrong action, that is a whole different level of problem. This step just massively expands the risk, and you have to approach it with, well, the utmost care. And that brings us to our final section. Section 5. We've basically arrived at our skyscraper's central control room. We've built this incredibly powerful, unbelievably complex system. So now we need an equally sophisticated way to watch it, to understand what the heck it's doing, and to learn from how it's actually performing out there in the real world.
So this right here illustrates one of the absolute trickiest parts of running a live AI system, something called drift. What it means is your AI's behavior can change even when you haven't deployed any new code. It's wild. A developer might make what seems like a tiny fix to a prompt, or maybe users just start talking to the AI in a new way. Or, and this is a big one, the company that provides the underlying model, like OpenAI or Google, might push an update. Suddenly, the ground is literally shifting under your feet. Now, this is what I find really fascinating. How these systems actually learn from us. You've got explicit feedback, right? That's the obvious stuff, like giving a thumbs up or a thumbs down. But then there's implicit feedback, and this is much, much more subtle. The system is learning when you hit regenerate response. It's learning when you accept a code suggestion it made. It's learning when you actually buy the thing it recommended. So it's not just listening to what you're saying, it's watching what you do. But there's a dark side to this feedback loop. It's the classic filter bubble problem, but on steroids. Think about it. The system can only get feedback on the stuff it actually shows you. So if it shows you 10 blue shirts and only one red one, and you happen to click a blue one, the system learns, aha, people love blue shirts. And what happens is these tiny little early advantages can just compound and compound over time, pushing the whole product into a really weird, biased state. And that leads us to our final and maybe most provocative thought. If you just blindly optimize for what users seem to like, whatever gets the most clicks or the most thumbs ups, you can accidentally train your AI to reinforce things that are just plain wrong. It can amplify popular myths or even straight up lies. Because let's face it, sometimes the truth just isn't that popular. And that is the incredible tightrope that AI engineers have to walk every single day, finding that perfect balance between what's useful and what's true. Thanks for joining us.